Good morning, good afternoon, and good evening. I'm very happy to present my research for the IEEE MTT-S International Microwave Workshop Series on Advanced Materials and Process for the RF and terahertz applications. I'm a visiting research fellow from the Imperial College London and a research fellow from the University of Southampton. Today, I will present my research into 60 GHz optimized nickel-free gold-plated enclosed coplanar waveguide liquid crystal phase shifter. I will first outline the research background, the technological gap, and the motivation of this research. This work aims to realize 60 GHz electrical beam steering, for which tunable phase shifters based on liquid crystals are designed, fabricated, and optimized. Specifically, we mitigated insertion loss by gold plating of an optimized thickness that is suitable for both the liquid crystal technology and the millimeter wave technology. During the design and simulation, we compared the conventional surface impedance model without meshing inside metals versus the method with meshing inside metals, and we found that for conductor thickness well above the penetration depth, surface impedance model is working fine with the advantage of a reduced computational burden. But for structures in which the penetration depth is of the same order as the plated conductor thickness, substantial errors occur in the loss estimation. In this situation, meshing and solving inside the plated metal can accurately represent the field's decaying behavior without overestimating of the conductor loss. In addition, the experimental consideration about the copper migration into gold and oxidation was investigated. Finally, we will show the measurement results of a number of our fabricated devices with different gold plating thickness to verify our findings of the optimum nickel-free gold plating. Let's begin with some research background. Arguably, the availability of 60 to 90 GHz spectrum is promising in response to a rising demand for the bandwidth. Historically, large electrically steered radars were deployed for mixed-site detection, guidance, tracking, and fire control. In addition to this military sector, phase array antennas also exhibit a huge commercial potential in the 5G, wireless communications, satellite communications, navigation at 60 GHz, intelligent transport at 63 and 64 GHz, as well as the 77 GHz automotive multi-beam long-range radars for adaptive cruise control, and 79 GHz monopath short-range radars for vehicle collision avoidance alarm and traffic monitoring. Conventional beam scanning by parabolic reflector satellite dishes are based on mechanically rotating the antennas. The top right figure shows a radar dish decommissioned for air traffic control at London Heathrow Airport. These large, bulky, mechanically controlled parts are vulnerable to inertia and vibration, resulting in poor reliability and high maintenance cost. Instead, there is an increasing demand for electronic beam steering by phase array antennas like the one shown on the bottom right, a static solution. Adaptive array smart antennas can allow steering of the beam to a given direction of focus without mechanical rotation, but just by changing the excitation phases of each radiating element. Accordingly, phase shifter would be the key component in a phase array. There have been a variety of methods to realize the phase modulation in the microwave and millimeter wave regimes. Existing microwave switchable techniques such as RF MEMS and solid-state PIN diodes offer ultra-fast but resolution-limited phase modulation due to the binary nature. Continuous analog phase shifting can be achieved by putting the continuously tunable dielectrics, like liquid crystals, in a guiding structure to change the wave speed and hence the output phase of the transmission line. Liquid crystals have been demonstrated with decent dielectric tunability and low dissipation factor, particularly at the millimeter wavebands. The dielectric tunability of liquid crystal is due to its molecular shape anisotropy, and hence the dipole moment variation from the perpendicular state to the parallel state with an applied low-frequency bias field from below the Friedrichs transition voltage to a saturation one. The variable polarization allows the continuous tuning of the dielectric constant and therefore a differential phase shift when interacting with a millimeter wave signal propagating over the delay line. With a decrease of the wavelength from microwave to millimeter wave, device performance degradation less observable at the microwave can be noticeable in the millimeter wave. To our knowledge, high insertion loss at millimeter wave remains the key challenge of liquid crystal planar phase shifter when comparing with the competing waveguide technologies. In my previous work in tunable delay line phase shifter based on highly anisotropic liquid crystal as tunable dielectrics, I have pushed the limit of the planar microwave transmission line implementation from the 10 GHz microstrip to 60 GHz enclosed coplanar waveguide, and progressively towards 90 GHz high aspect ratio coplanar waveguide that can challenge the current status of manufacturing in terms of electrode patterning and the liquid crystal alignment. For practical performance measurement of my previously fabricated liquid crystal device, higher than expected metal loss occurred because of the accelerated copper oxidation during the alignment agent baking process not discovered at the design stage. Therefore, there is a need for a surface finish by gold plating in this study, compared with the traditional electrolysis nickel immersion gold ENIG-based surface plating method, which is highly lossy due to the resistive nickel barrier. This work reports a novel nickel-free gold plating of an optimum thickness directly on the copper for a low-loss ECPW LC phase shifter at 60 GHz. Modern computational electromagnetic software packages take the representation of the conductors by default as a surface impedance model. This treatment only performs meshing and computing the fields at the conductor surface and in the space outside the conductors, but the space inside the conductors is not meshed. The effects of the internal fields are considered by a surface impedance model, given that the internal fields fall exponentially with the distance from the surface. We perform a 60 GHz simulation for the liquid crystal-based ECPW with the copper thickness of 70 microns, which is 65 times of the skin depth of copper. Gold plating is not considered first. Comparative study on insertion loss calculation is conducted based on two models. Model 1 based on HFSS default surface impedance model with star meshing inside metals. Model 2 is adaptive meshing inside metals and solving the internal fields of metals, refining the volume and surface meshes where the field gradients are high. So convergence of the adaptive meshing refinement inside the core line metal is shown in this figure. Benchmarking the two different models we verified that S21 given by the surface impedance model without meshing inside metals agrees with that by meshing inside conductors in this case. However, it is not the case for a thin layer of gold plating on a copper pattern. For the same liquid crystal-based ECPW geometry, we simulated gold-plated copper with gold thickness changing from 0 to 4 microns, which is from 0 to 60 times of the gold scheme depth at 60 GHz. Simulation results in the figure here presents that S21 versus the ratio of the gold plating thickness to gold scheme depth at 60 GHz. It is clearly observed that the traditional surface impedance model fails to accurately model the gold plating cases when the gold thickness is thinner than 4 times of the gold scheme depth. Instead, it overestimates conductor loss by up to 0.3 dB per cm. S21 levels off when the gold thickness is thicker than 4 times of the scheme depth, beyond which both models agree with each other in statistics. Furthermore, from this figure, the addition of the gold finish degrades S21 due to the increased resistance as compared with the non-plated pure copper, assuming oxidation is not happened. However, at the elevated temperature when baking the liquid crystal's alignment solvent, an inadequate thickness of pure gold deposited on PCB can result in a diffusion of copper atoms into gold, exposing the copper, and ultimately a formation of oxide layer, which degrades the electrical conductivity, as demonstrated by the experiment results shown in the figures on the right. Here, different thickness of the gold plating from 0 to 3 microns are experimentally investigated for an array of coplanar waveguide substrates with 0.5 ounce of copper foil. So figure 4 here shows the gold-plated substrate at room temperature. After 200 degrees of baking for 20 minutes, the same groups of substrates are inspected again, with the profiles illustrated in figure 5. Compare the figure 5b with the figure 4b for the 50 nanometers gold-plated substrate. Tarnishing occurred at about after the 200 degrees heating as the copper atoms migrate into gold, which is an irreversible process, and raise a problem of copper oxide layer formation and dramatically increase the resistance. As evidenced by the insertion loss measurement shown later for the assembled phase shifter with different gold plating thickness, but with the same delay line length for the pi shifting at 60 GHz. Out of the concern of the copper migration and the malfunctioning, the plated gold should be thick enough compared with the copper foil underneath. However, the etching and the plating errors both increase dramatically with the plating thickness, resulting in a substantial deviation from the ideal right-angle design of the conductor profile. Optimization of the gold plate thickness in this study is arguably a compromise upon the theoretical insertion loss and the practical limitation from the liquid crystal-based device manufacturing process. Here we outline the device prototyping process for the lithography, patterned copper-based substrates are the surface finish with the gold following a nickel-free electrolytic process. Thickness of the gold plating is experimentally investigated for reliable protection without degrading the conductor's performance, especially after the 200 degrees baking. Finally, we showed the measurement results. For devices with the non-plated copper conductors, the maximum deterioration of the insertion loss is up to 4.5 dB at the 67 GHz when compared with device plated with 2 microns. This indicates that relying purely on the alignment layer has a limited scope in preventing oxidation of the bare copper. The insertion loss degradation is even worse for the 50 nanometer gold-plated device above 65 GHz, as the coexistence of the tarnishing and oxidative effect exacerbates the increase of metal loss by 3.5 dB at 67 GHz as compared with the non-plated device that is oxidized but not tarnished. The increase of the plating to 2 microns reliably addresses the elevated metal loss problem caused by this oxidation and tarnishing, as verified by this wideband improvement in the S21 across 54 to 67 GHz. It is experimentally verified that 2 microns can suffice to reliably deter the copper oxidation, while degrading S21 by only 0.1 dB compared with a bare copper-based device simulation, assuming no oxidation. Beyond this plate thickness, S21 exhibits no further benefits, but could be worse due to the increased trapezoidal effects. Our optimized device reports a figure of merit of 60 degrees per dB at 60 GHz, which is a significant improvement by 42 degrees per dB as compared with other people's work. In conclusion, this work numerically investigates and experimentally optimizes a novel nickel-free gold-plated ECPW LC Phase Shifter at 60 GHz. By comparative analysis of adaptive meshing inside metals versus the surface impedance models without meshing inside, we derived the threshold that the conventional surface impedance model is invalid. Amplification of this can be expanded for a wide range of the millimeter wave components, such as filters, antennas, couplers, with the plating thickness comparable to the penetration depths. Thank you for your attention. Please feel free to contact me if you have any questions.